All right, everyone. So now it's time for the modeling data distributions unit test. So first question here is we have a stem and leaf plot, and they ask us to estimate the percentile for a hydrangea head with 5.2 inch diameter. The idea here is there are 35 total points, and 5.2 would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, the 13th value. All right, now from there, if we want to calculate the percentile for 5.2, all we have to do is figure out how many values are less than or equal to 5.2. And that's going to be, well, there's 13 divided by 35. So that means 37. Right? Hooray. One thing, I'm going to look at the step-by-step solution. Yeah, that's what they do. So it's observations that are less than or equal to. So include the place of the value itself. So in other words, you're including 5.2 when you're counting up to the values. And if there were more than one 5.2, then you would add all of them. All right, not just the first. All right, up next, now we get to start talking about the normal distribution, which is kind of the fundamental of the rest of the course. So, okay, so here's one thing that we all definitely need to consider now. Before, when we were doing this, we would usually rely on the calculator in normal CDF. However, if you're at home right now and you don't have a graphing calculator, it's now time to totally understand how the z-table works. So, when it says they want to know who's in the top 15%, if it's normally distributed, then the top 15%, usually I'll put my percents up top. So if there's 15% here, well then that means there's guaranteed to be 85% below. And the reason I care about this 85% below is because the z-table, if you look, shows you the area to the left of what you want. So in other words, we want the area to the right, which is 15%, but the z-table will tell me where there's 85% below. And the other thing you can see here is that clearly we're going to be above the halfway mark. If there's only 15%, 50% would have been right here. We're larger than that. We're looking for this z value right here. And so from there, that means we're going to have to go to the backside because this is only telling us areas to the left of the middle. So we flip it over. Now we're to the right of the middle. And what we're actually doing is we're looking for 85% as a decimal in the middle. And the closest we get to that is right here. And that is 1.04. So this z-score is 1.04. And what we want to do is we want to figure out the corresponding SAT score for that z-score. So if our z-score is 1.04, remember that a z-score is calculated by your particular value minus the mean of all the values, which is 1,497, divided by the standard deviation of the values, which is 322. And so now what we're going to do is we're going to multiply the 322 to get it out of the denominator, just to have x minus 1,497 left. And then the way we would get x, the value we want, is we would add the 497. And so we get 1,831.88, which corresponds to answer choice D. All right, and so big takeaways from this last example is that a z-score this z-score comes from an actual value, in other words, your value that you're interested in, minus the predicted value, or the mean, divided by the standard deviation. That's what a z-score is, the actual minus the predicted, divided by the standard deviation. All right, up next we have an empirical rule question, and it says that the lifespan of seals in a zoo are normally distributed, and the average is 13.8, and the standard deviation is 3.2. And then it says use the empirical rule to estimate the probability of a seal living longer than 7.4 years. So the thing to do is figure out how 7.4 is related to this 13.8 and 3.2. And you can get 7.4 by subtracting 3.2 twice. All right, so in other words, what that means is 7.4 is 2 standard deviations below. And so what I'll do is I'll draw out this picture for you. Now this would be -1 standard deviation plus 1 standard deviation. The idea is there's 34% on either side. And then when you get to -2, just in this little individual block, there's 13.5%. And I don't remember what the last percentage is, but we don't really need it for this problem, because we want to know the probability that a seal lives longer than -2 standard deviations. Because again, 7.4 is -2 standard deviations on the z-score table, which is the normal distribution. So if we're at -2 and we want to know how much more then, here's all we have to do. We have to remember that from the middle to the right, there's going to be 50%. And then we also have this additional 34 and this 13.5. And so when you add the 50% all above the middle, this 34% and this 13.5%, you're going to get, I believe it's going to be, looks like 97.5%. All right. And so the big key here is, how am I getting 34 and 34? Well, because if in between plus or minus 1, 68% of the data is there, well then if you have to split that in half, 68 split in half is 34 each. And then to get 95, there's 45 and 45, but since you've already used up 68, there's only 27 left to fill in those remaining 2 slots, and so on and so forth. All right. Up next, it says find the percent of the area under the density curve where x is less than 3. And really what that means is we need to take a look at this small triangle right here. Here's 3, here's 1, this is 0.6, and if you kind of see how this is counting, then this is going to be 0.4, and this is going to be 0.2. The idea is we want the area less than 3, which really means we want the area of this triangle. So this is definitely geometry. We have a base, which goes from 1 to 3, so the base length is 2. We have a height, which is 0.4, and the area of a triangle is 1/2 times base times height, and so that's just going to end up being 0.4, which is 40%. All right. Up next, it says a set of computer science exam scores are normally distributed with a mean of 71.33 and a standard deviation of 3. What proportion of exam scores are between 68 and 77.99? So this is a question where you definitely do want a graphing calculator because it would be so easy. But what we're going to have to do is we're going to have to find the z-score of 68 minus the mean divided by 3, and we'll also have to find the z-score for 77.99 minus the mean divided by the standard deviation. I think I brought my calculator with me when I moved rooms. Yep, here it is. So, I mean, I still have a calculator, but I'm going to use it as a basic graphing calculator, or as a basic calculator for what you might have at home. Make sure you actually divide that first and then subtract and then divide it by 3. So the lower z-score is negative 1.11, and the larger z-score what was it? It was 77.99. And then that divided by 3, we get z equals 2.22. And what we need to do now is we need to use the z-table and find out how much area is to the left of negative 0.11, negative 1.11, and that is 0.1335. And then all the area left of 2.22 is 0.9868. And the idea is what I've just done, that's a very bad normal distribution. What I've just done is I figured out how much area is to the left of negative 1.11. I figured out how much area is to the left of 2.22, and I'm going to subtract those amounts, and then I'll get the area in between. So 0.9868 minus 0.1335, I get 0.8533, and there you go. Now, just to show how easy this can be, if you do have a graphing calculator, you're just going to go to second, distribution, normal CDF, and the lower is just the lowest data point, 68. The upper is the upper that you want, the 77.99. The mean is 71.33, and the standard deviation is 3. And there's the answer without all the work. So there you go. Just remember that if it said higher than 68 or lower than 77.99 or something like that, usually what you do in that case is you choose the lower or upper value, the one that's not given, to be either like negative 1 million or positive 1 million as you work through it.